Okay, we're going to go through this example. A 0.5 kilogram ball is dropped from a 10-meter height. Calculate the work done on the ball between the moment it is released and when it hits the ground. So the main thing we need to know, let's just review a couple of ideas here. First off, we know that work is equal to force times displacement. There's no mention of force here, there's none of that. So what we also need to remember from before we took our break is that work is also equal to the total mechanical energy which is equal to our gravitational potential energy plus our kinetic energy. So, continuing with this sort of review notion, we know that gravitational potential energy is equal to mass times gravity times height, and that kinetic energy is equal to 1/2 mv squared. So those are sort of a review of some of the formulas that we've looked at in this unit. So now let's write down what we know. We know we have a 0.5 kilogram ball. So mass is equal to 0.5 kilograms. We know that our height is 10 meters. Now normally we would write this as displacement, but if we look here, we're talking more on around height thing. It's the same general idea, we just call it a different letter now. So height is equal to 10 meters. Now there's no other number sort of information given here. So I'm just going to sketch our problem here. We're going to drop our ball. Oops, sorry, I'll move the camera. Drop the ball and it's going to fall. And so two things that we know is that at the top right here, we know that our gravitational potential energy at the top before we drop it is max. And as this object falls, our gravitational potential energy will decrease as the speed increases. And when we get to the very bottom, we know that our kinetic energy is maxed. And so when that's maxed, it means that there's no potential energy. And we know that our total energy, which is also our work done, is equal to the sum of our gravitational potential plus our kinetic. So what this essentially means that if we find out what our potential energy is here at the top, we know that our kinetic energy is equal to 0 at that point, which would mean that all of the energy in the system would be gravitational potential energy, which would mean that that would be our total work done, which would mean that we would actually be finding our work. So let's see what this looks like. I only know two numbers here, m and h. And if I look at my formula, I need to know m, g, and h. So even though it's not noted in the question, we always know that g is equal to 9.81. I'm not going to worry about the negative at this point in time. I'm just going to write 9.81. Okay, so then I have E is equal to mgh. I'm going to substitute in. I have 0.5. 9.81. I just realized I don't have a calculator with me. So let's see, that's going to be 98. So that's almost 100. So 50, I don't know, around 40 something. Hang on a second. Just grab an online calculator here really quickly. Okay, so I have 98.1 times 0.5. Oh, okay, that did not, obviously my number lock was not on. Good Lord. Okay. Sorry, I don't know why this is so complicated. 98.1 times 0.5. I should have been able to do that in my head. I apologize. 49. Okay, it's 49.05. I'm just going to take 49. Okay. Now, we also need to remember that the unit for energy is joules. And so gravitational potential energy is 49 joules. So I know that my work done is equal to EK plus EJ, or EG. I know that at the top right here, it is not moving. And if it is not moving, then I have 0 kinetic energy. And so I have 0 plus 49. And while this might have seemed like a more complicated question, when it asks for the total work done in the scenario, it really was just a very straightforward calculation if we understand that the work theorem says that we have that work is equal to our total mechanical energy, which is equal to the sum of those two parts.